All right, in the next few concepts, we're going to be focusing on something called electrochemical cells. And today we're going to focus on the ones that have spontaneous reactions involved, which are referred to as voltaic cells. In redox reactions, we know there is a chemical reaction taking place in exchange of electrons between particles that are being oxidized and reduced. A practical use of this, so how we can apply this, is to something called an electrochemical cell. Now, the two types, we're going to focus on voltaic today. That's a spontaneous chemical reaction that produces a flow of electrons. And then in a couple of concepts, we'll talk about and focus on an electrolytic cell that actually requires an electric current to force a non-spontaneous reaction to occur. So let's just focus on a voltaic cell, which is actually going to convert chemical energy into electrical energy. And a great example of this is a battery. Now, a voltaic cell has many working parts that are involved, such as you can see in this diagram something called a voltmeter that measures the flow of electrons, a salt bridge, we have electrodes. But let's just first look at the two reactions taking place, and each container is referred to as a half cell. And we've talked about half reactions. One, oxidation is going to occur in one half cell, and then reduction will be occurring in the other half cell. Now, zinc here is getting oxidized, and we can see that this is going to be referred to as an anode. We'll talk about that in a minute. And then copper, which is gaining electrons in its half cell, is going to be the metal that's getting reduced. So what happens is zinc is going to be releasing or losing electrons. Those electrons are going to be traveling through the wire and arriving at the copper electrode, and thus combining with the copper ions. So let's talk a little bit more about the working parts. Those metal strips are called electrodes. So this bar right here of zinc is an electrode, and the copper on the right is an electrode. Now, where we have copper right now, that's called our cathode. That's where reduction is occurring. A common phrase for this is red cat, reduction at the cathode. This is referred to as the positive electrode in a voltaic cell, and it's always the less active of the two metals involved in table J, which means it's lower on table J. This is going to spontaneously attract electrons to it. So remember, reduction is the gain of electrons. So in our cathode, it's actually attracting the electrons to it. Now, interestingly enough, the metal electrode for the cathode becomes larger over time as the atoms stick to it. Take a look at our formula. We have these copper ions that are in solution. They're going to combine with the two electrons that are going to travel to the electrode to produce solid copper. And those are going to be forming and building up on the cathode. Now the anode, which is on the other side, and in this example zinc, this is the electrode where oxidation is occurring. A common phrase for this is an ox. Anode has oxidation occurring. This is referred to as the negative electrode in a voltaic cell, and this is the more active of the two metals in the cell. And this means it's higher on table J. This is going to spontaneously lose electrons that will travel through the wire to the cathode. And unlike the cathode, which builds up on its electrode, this one is actually going to be becoming smaller over time as ions dissolve. So that's those solid copper atoms are going to lose electrons to become copper ions in solution. And you can see that in the diagram. Now, one important part to note is that electrons are going to always flow through the wire from the anode to the cathode. So I always remember this alphabetically: anode to cathode, A to C. And it's important to note that electrons are always through the wire, never through what we've referred to as the salt bridge. So an ox, anode, is always where oxidation occurs, and then red cat, reduction always occurs at the cathode. And then also remember the phrase, the red cat gets fat. The cathode is always going to be building up in size from the atoms that are basically sticking to it. Right, now the salt bridge, which you might have noticed in the diagram, is a crucial part to a voltaic cell that provides a path for the flow of ions, not electrons, but ions, between the two half cells. Or else what would happen is that these half cells would become unbalanced and then stop the flow of electrons, thus not having electricity generated up to that point. So this prevents a buildup of charge. Now take a look at the two half cells. On the anode side, on the left, this is building up a positive charge because those positive zinc ions are getting put into solution. So in the salt bridge, a negative ion that they've placed in the salt bridge is going to migrate its way to that side in order to balance out the positive that's building up. On the right-hand side, we're taking out positive ions and reducing them on the cathode. So we start to have a negative charge of ions build up in this case, the right half cell. So in the salt bridge, the positive ion is going to migrate over to that side to try and balance out the negative ions that are being left and building up in solution. So again, the salt bridge allows for an ion migration and prevents the buildup of charge in the half cells. Another example of this is a porous barrier. It allows positive and negative ions to flow through it in order to balance the two half cells. Now, how can we tell which metal will be oxidized and which will be reduced? Well, we can use table J in order to decide. The higher on the table, the more reactive it is, and this means it will replace anything below it that is in a compound. So this goes back to our single replacement reactions. Now, anytime we have a metal involved, it's only going to be able to replace a metal in the compound. The metal by itself has to be above the metal that's in the compound. So in this case, CS is above Mg on table J, so this will actually occur to create magnesium and then cesium chloride. However, magnesium is not above CS, or cesium, so there's no reaction. Now, this one's a little bit trickier usually for students. Our element that's by itself are nonmetals. So we're actually using the right-hand side of table J, and we're looking to replace either Cl or Br. Now, Br is not above Cl on table J, so this will not occur. However, Cl is above Br, so Cl is reactive enough to replace Br, and thus creating bromine and lithium chloride. And we'll practice this a little bit more in class tomorrow as well. So a general rule to keep in mind is for metals that are on the left of table J, the higher on table J, the more easily oxidized. For nonmetals on the right of table J, the higher of the four on table J is more easily reduced. And this goes back to, remember, metals like to lose electrons, nonmetals like to gain them. So the more reactive they are, the more they'll follow the idea that metals will be oxidized if they're more reactive, and nonmetals will be more easily reduced if they're more reactive. So these little keys here are just for the metal side. The reverse would be true for the nonmetals. So the higher metal is the more easily oxidized metal, and thus going to be the anode site. The lower metal, which is the metal that's going to be reduced in the voltaic cell, is going to be the cathode site. So in a voltaic cell, the metal that is higher in the chart will be oxide and is thus the anode, and the lower metal is the site of reduction and will be the cathode. All right, so we're going to practice a little bit. This is a common diagram. I've already started to figure out by using table J that Ni is higher on table J and Ag is lower on table J, which are two very important hints for answering these questions. So using table J, we're going to predict the direction of electrons that will spontaneously flow and draw the arrows to indicate on the diagram. Well, remember, the one that's higher on table J is more easily oxidized and thus going to lose electrons. So they'll be leaving the nickel electrode, which is getting oxidized, and traveling over to the silver electrode where reduction is occurring. So oxidation to reduction, or anode to cathode. The electrons are going to flow, in this case, from nickel to silver. All right, looking at number 4 and 5, at which or in which half cell does reduction occur? So because Ag was lower, we know that reduction is going to occur in the half cell containing silver. And then the opposite is true. Where is oxidation going to occur? Nickel is higher on table J, so that is where oxidation is going to occur. Thus, we can answer 6 and 7. The cathode is where reduction occurs, so silver. And then which electrode is the anode is where oxidation is occurring, so nickel. And then finally, assigning our negative and positive electrode. Remember, the negative electrode is your anode, so in this case nickel, and our positive electrode is going to be our cathode, which is silver. Okay? All right, so we will talk a little bit more about this, and obviously not even just a little bit, but a lot more about this in class tomorrow. We'll focus on analyzing various diagrams of voltaic cells and applying these notes to different examples. All right, so no quiz or summary, just go ahead, review your notes, and come ready to class.